Bernoulli's equation. How do we relate the pressure, velocity, and height in a flowing fluid? We have a duct which has varying cross-sectional area and varying height. A fluid enters with velocity v1, pressure p1, and elevation which is measured from some arbitrary reference value, z1. The fluid leaves the duct at velocity v2, pressure p2, and elevation z2. We are going to assume that the fluid is inviscid, that it has no viscosity. If we make this assumption, then there are no frictional losses as the fluid flows, which means that there are no irreversibilities. The flow, therefore, is isentropic. Let us also assume that the fluid is incompressible. For an incompressible fluid, we know that the change in entropy, delta S, is equal to C, which is the specific heat, times ln of T2 upon T1, where T1 is the temperature at the entrance and T2 is the temperature at the exit. For isentropic flow, delta S is equal to 0, the entropy remains constant. And therefore C times ln T2 upon T1 is equal to 0. As a result, T2 is equal to T1. The temperature of the fluid remains constant. Isentropic and incompressible flow therefore implies that the flow is isothermal. For incompressible substances, we know that delta H, the change in enthalpy, is equal to C times T2 minus T1 plus V times P2 minus P1. If the process is isothermal, T2 is equal to T1, and that first term goes to 0. Delta H is therefore equal to V times P2 minus P1, where V is the specific volume, and P2 minus P1 is the change in pressure. The specific volume is equal to 1 upon rho, which is the density. So the enthalpy change we can write as P2 minus P1 divided by rho. The duct is a controlled volume. We can therefore write an energy balance for it, where the energy going into the controlled volume is Q dot plus W dot plus M dot times H1 plus half V1 square plus GZ1. And this equals the energy leaving, which is M dot times H2 plus half V2 square plus GZ2. There's no heat crossing the control volume boundary, so the first term goes to 0. There's no work crossing the control volume boundary, so W dot equals 0. We can therefore write that H2 minus H1 plus V2 square minus V1 square by 2 plus G Z2 minus Z1 equals 0. We just showed that H2 minus H1 equals P2 minus P1 divided by rho. Substituting that, we can write that P2 minus P1 upon rho plus V2 square minus V1 square upon 2 plus G Z2 minus Z1 equals 0. Taking this equation, we can rearrange it so that all the terms at the inlet are on the left-hand side and all the terms at the outlet are on the right-hand side. We therefore have P1 upon rho plus V1 square upon 2 plus GZ1, and this equals P2 upon rho plus V2 square upon 2 plus GZ2. This means that the sum of these three terms, P upon rho plus V square upon 2 plus GZ, are the same both at the inlet and at the outlet. But since our definition of the outlet is quite arbitrary, we could have defined that as being any point in the flow. The sum of these three terms is always conserved. Therefore, we can write that P upon rho plus V square upon 2 plus GZ is equal to constant. This is what we call Bernoulli's equation. Bernoulli's equation is very useful in relating changes in pressure and velocity along a flow. Here we have a duct whose cross-sectional area suddenly reduces. This means that the velocity must increase. We have attached two tubes to the different sections of the duct, and these act as manometers. The fluid rising in them tells us how much the pressure is. The height along the duct is relatively constant. We can therefore ignore changes in Z, and Bernoulli's equation simply becomes P upon rho plus V square upon 2 is equal to constant. Therefore, in the first part of the duct, where we have low velocity, we have high pressure. In the second part of it, we have a high velocity, which means that we have low pressure. And we can see this change and measure it by the height that the fluid rises in those two capillary tubes. To summarize, if the fluid flow is isentropic and incompressible, then we can write Bernoulli's equation, which says that P upon rho plus V square upon 2 plus Gz is equal to constant.